let's take a look at these bell ringer questions. So we're going to kind of ignore this right now. You did some phase diagrams yesterday. Hopefully those made sense. I didn't get too many questions about them, so hopefully you were able to figure those out. What effect does pressure have on boiling point? So if you increase the pressure, the boiling point is going to increase. So they are directly proportional. Okay? What effect does elevation have on pressure? So remember, when you go higher in the atmosphere, if you climb a mountain, for example, if you increase elevation, the air is thinner. And so if the air is thinner, it is going to have less pressure as you increase elevation. Okay? And then the last one, what type of force exists between the particles of a liquid holding them together? So we talked about that yesterday, and that is an intermolecular force between different liquid molecules. Okay? Intra is in between one molecule, like an ionic or covalent bond. So today we are going to talk about a couple of more properties of gases, and we are going to do some calculations with some gases and look at some more relationships between them. So one property of a gas is that it's compressible, meaning we talked about how gases assume the shape and volume of their containers, so you can compress them. When you buy helium, if you bought a tank of helium, that helium is compressed in that tank. When you use it to fill up a balloon, it's going to fill up a lot more balloons than what it looks like. So I have a small helium tank in my garage, and it's maybe 2 feet high and like maybe a foot wide or so. And so if you look at it, you think, well, that can only maybe fill up like 3 balloons. If you compare like size-wise, the size of a balloon versus the size of the tank. But in that tank, that gas is compressed. And so actually there's like enough gas in that tank to fill up like 25 or 30 balloons, because when it's released into the balloon, it's not compressed anymore. And so just a small amount of gas molecules are released relative to what is inside there. So gases are compressible when they're put under pressure. To be able to take up a smaller volume. Okay, so some factors that affect gas pressure. We are going to do calculations with all of these, but not all of them today. So the first is the amount of gas. That's going to affect the gas pressure. Okay. And so if you increase the number of particles, that's going to increase the pressure. Just like we talked about the other day, if you have our classroom and we moved out all the furniture and we had 10 people in there, it's not going to feel very tight. You're not going to feel squeezed or packed in. But if we put 30 people in there, you're going to feel more squeezed or packed in. The people are like the particles, right? And so the way that you feel squeezed or claustrophobic or whatever, that's kind of like the pressure. And so if you increase the number of particles, it's going to make that pressure increase, okay? Volume. If you increase the volume, it's going to decrease the pressure, okay? So let's think about this analogy with my classroom again. So if we increased the volume of my classroom, so let's say we blew out that wall that separates my room and Mr. Lefevre's room, and so now my classroom is twice the size as it normally is. That's going to decrease the pressure because we have a lot more space and everybody can spread out more, okay? So if we increase the volume, we decrease the pressure. The gas or the people would be less compressed or cramped in there, and it's essentially exerting less pressure on the container in the room. And then last is temperature. So if we increase temperature, we increase pressure, okay? And so remember, temperature again is a measure of kinetic energy. And so if we increase the temperature, those molecules, those particles are going to move faster. They're going to be bumping into things more often. They're going to be bumping into the walls of the container more often, and so that's going to increase pressure. So the amount of gas, that's a directly proportional relationship. The temperature of gas and the pressure, so let's look, temperature and pressure, amount and pressure. The one that's different is the volume. Oh, I drew that wrong. Cross that out. Okay, I should have drawn it the other way. Sorry. The pressure and the volume. Okay, those are an indirectly proportional relationship. All right. So that's important to remember. Let's see if I can get to my next slide here. Okay, so we are going to talk about 2 gas laws today, and you have a worksheet in your binder that has these 2 gas laws on it. And so those are Boyle's law is the first one. And so just as we said just a moment ago, there's an inverse relationship between pressure and volume. And that's what we drew in our graph. Pressure and volume, it's an inverse relationship. So for example, as the pressure goes up, as the volume goes up, the pressure is relatively small, okay? As the pressure goes up, the volume is relatively small, all right? And so Boyle's law is summarized in this equation. P1 times V1 equals P2 times V2. Or sometimes you'll see it without those X's in there. Just P1 V1 equals P2 V2. Okay? So let's do a little practice with this. A high altitude balloon contains 30 liters. All right? So I'm going to underline that. We know that is a volume. Liters is a volume. So I'm just going to label it as volume 1. Okay? Of helium gas at 103 kPa. kPa is a pressure, and I'm going to label it pressure 1 because it was affiliated with that volume 1. Okay? The next sentence, what is the volume? So we're trying to find a volume. So we're trying to find volume 2. When the balloon rises to an altitude where the pressure is only 25 kPa. So that's will be our P2. Assume the temperature remains constant. Okay, so we're going to use this formula, V1P1 equals V2P2. And we will just plug in and multiply. So we've got 30 liters times, 103 kPa equals V2, that's what we don't know, times 25.0 kPa. Okay? And so essentially what we're going to do is multiply 30 times 103, and then we're going to have to divide by 25, just like you would in algebra, how we divide to get the V2 by itself. Okay? And that'll cross that out. And you'll see that the units are going to cross out here as well. And so whatever you get, your answer will be in liters. And because it's a volume, we know that it should be in liters. So I'm going to plug this in my calculator. 30 times 103 divided by 25. And I got 123.6 liters. And that should be pretty easy for you guys to do. Okay, it's just a plug and chug, putting the things in the right spot. Okay. So, let's see, I can't get to my next slide here. All right, you have a couple to try. I'm going to pause the video and we'll come back just in a minute and look at these together. All right, so let's take a look here at these problems. For the first one, you should have got 6.48 liters. So just plugging in everything, P1 would have been 105 kPa. P2 would have been 40.5 kPa. And then V1 would have been 2.5 liters. And so when you solve for V2, you should have got 6.48. Just multiply 105 times 2.5 and then divide by 40.5. Okay? The second one was very similar, except we were solving for P2. And so multiplying 205 as your P1 times 4 as your V1, and then dividing by 12 liters, which was V2, should have left you with a P2 of 68.33 kPa. So hopefully you all got those correct without any issues. Okay, so that was Boyle's law. We're going to look at one other law today, and that's called Charles's law. And so Charles's law says that the volume of a fixed mass of gas is directly proportional to its Kelvin temperature if the pressure remains constant. Okay, so remember we said the volume of a fixed mass of gas is directly proportional to its temperature in Kelvin. Okay, if the pressure remains constant. And so that's how that would look here. So the formula for Charles's law, and again, you have these formulas on your formula sheet, is V1 over T1 equals V2 over T2. Okay? So let's put this one to practice and see what we can do with it. So now, one thing I want to say, and you may want to write this here, it's a Kelvin temperature, okay? So you have to convert to Kelvin. So if you're given the Celsius, you have to add 273 to get to Kelvin, okay? That's super important. If you do it in Celsius, it's going to be wrong. You have to do it in Kelvin, all right? So let's look at this. A balloon inflated in a room at 24 degrees Celsius, okay, so that's going to be a temperature 1, has a volume of 4 liters, so that'll be a volume 1. The balloon is then heated to a temperature of 58 degrees Celsius, so that'll be a temperature 2. And then what is the new volume? The question is asking us for a volume 2. Okay, so we're going to use our formula V1 over T1 equals V2 over T2. Okay, so my V1 is 4.00 liters. That's what I labeled that. My V2 is what I'm solving for. Okay, now my T1, I've labeled T1 up here 24 degrees Celsius, but I have to add 273 to that to be able to convert it to Kelvin, and so that's 297 K. Okay, and then the other one, 58 degrees Celsius plus 273 is going to be 331 K. All right, now I'm not sure if you're comfortable with the math here, but basically what we're going to do is we're going to cross multiply. So we're going to multiply 4 liters times 331 K, and then we're going to divide it by what's left, which is the 297 K. And that's how you set these up, okay? Cross multiply the two that you have the numbers for. Okay, and then divide by the one that's left over. All right, so we're going to do 4 times 331 and then divide by 297, and that gave me 4.458, and the units, the Kelvin cancels out, should be liters, which we're solving for V2, so that makes sense, because a unit of volume is a liter. Okay, 4.458 liters. All right, now you have 2 practice problems to try, and then we can come back together and you can do these on, or we'll look at them together and see if you got them right. Okay, so let's take a look at these together. So the first one you should have got 3.39 liters. We were solving for V2. We plugged this in as our volume 1, the 6.8. Okay, we had to convert this to Kelvin, and so that was our temperature 1, and that was 598 Kelvin. this was our temperature 2, which was 298 Kelvin, and we solved for our volume 2. So we cross-multiplied 298 times 6.8 and then divided by 598, which should have given you 3.39 liters. Okay? The second one was very similar. Our volume 1 was 5. Our temperature 1 was negative 50 degrees Celsius. Don't drop that negative. So that made that 273 K. Our temperature 2 was 100 degrees Celsius, which was 373 degrees K. And then volume 2 here is what we were solving for. Okay, so when we set this up, we cross multiply 5 times 373 and then divide by 223. Okay, and you should have gotten 8.36. Now, I know in all 3 of the practices that we have done, we've kind of solved for the one that was up here at the top. And so every time we multiplied down and across. But please realize that you can do that if you had, I'm just going to make up numbers here. T1 and 30. I don't know. I'm literally making up like ridiculous numbers. Okay, that it doesn't matter how you cross multiply. You could cross multiply here and then divide by this one. Okay, you're always dividing by the one that's left by itself. Or you could, you may have to cross multiply this way. It doesn't matter. You just multiply the two that have one diagonal across from it and then divide it by the one that's left over. Okay. So that wraps up today's lesson. If you have any questions, let me know. And if not, then you all have a great day.